Hello. I think you can see the desktop. Let's see. Okay.
Yes, Professor.
Yeah. Okay, great. And okay, I got the chat up. And okay. So what we're gonna do today is talk about this new language, um, language 7. Okay, it's down here. We're gonna talk about language, start talking about language 7. And it's a big deal because this language introduces functions, which is the heart of the whole, essentially the heart of modern programming. Okay, so the idea of functions is really basic. So okay, now remember what we mentioned. We started talking about this a little bit the other day. We need to describe how to define functions, how to call functions. Okay, we need to describe how to define functions and how to call them. So these are the two parts of the language, one for defining functions and one for calling. Now, first, let's talk about calling real quick. Okay. I created a kind of a funny notation for calling. It's used in a few programming languages, but it's not a notation you've seen before. So I want to explain why that is. Okay, so if I have a function defined, I'm going to use math notation. So like x squared plus 3 times x. There's a function definition. And then here's what we mean by a function call. Okay, f of 3. Okay, now this is the notation now this notation is used by math, it's used by C, it's used by Java, it's used by most programming languages that you're aware of. Java, it's used by C++, JavaScript. Okay. Now it's not used by every programming language. Some programming languages do this. That would be languages like ML and Haskell and F sharp. They do it this way. They write the name of the function and then the parameter afterwards. Another example is this. This would be the notation in Lisp, Scheme, Closure. Closure. Okay. Our notation's closest to this one here. The one we're going to use is closest to that one. Okay, so that's the one we're going to use. Is something like that. Okay, now let me give my function more than one parameter. Okay, so then you would do something like f of 3, 4. Okay, in JavaScript, in Java. Now in Haskell, you would just write f3, 4 with spaces between the you put in those languages, you don't put commas between parameters. You don't wrap them in parentheses. You just put the name of the function, space, parameter, space, parameter. And if it was Lisp, Scheme, or Closure, you would write f of 3, 4. Okay. Now that looks like a tree. That looks like a tree with f at the root and the parameters down below. Okay, so that's essentially that's what we want. We want something like that. Okay, but there's a problem with this tree like this. It doesn't really work. So Lisp and Scheme and Closure are tree languages like what we're doing. Okay, and you would think that a function call would be a tree. Notice that that's a lot like. Notice how similar that is to writing the sum of 3 and 4. The sum of 3 and 4 is a tree. It's the plus tree with branches 3 and 4 below it. So if that's good enough for the plus function, why isn't it good enough for the f function? Okay, so this notation looks an awful lot like this notation. Okay, The trouble is functions can have no parameters. Okay, it's legitimate to have a function with no arguments. Yeah, so I can have a function like this. G, this is one of the problems. I can have a function g of x, g is equal to, say, 5, just a constant function. It doesn't take any inputs and it returns 5. It's just a constant function. What in C and C++ you call a void function. Like in the old-fashioned C, you would write void in here to say there's no parameters in this function. In the old days of C, you actually had to write void in there to say that there's no parameters. Okay. Now, you would call this function in Java like this. You would call it in ML just by doing that, and you'd call it in Scheme by doing this. Okay, but that's not a tree anymore. See, now it's just it's kind of weird. Now it's just a root, but you see it's using tree notation, but it's not. But there's no branches. And this actually causes glitches in the parser. Whoops! Oh, I should switch to G here. Okay, that's not really a tree. Okay, notice that this is a tree. Yeah, and this is a tree. That's what Lisp, Scheme, and Hash and Closure. Lisp is the language that invented this idea of programming in trees. Yeah, they invented this prefix notation, which essentially is a programming in trees. But it kind of screws up when you get to a function with no parameters. Okay, when you get to a function with no parameters like this, yeah, that's okay here. That's okay here, but it's not a tree here. So what I switched the language to was that the way you call a function in our language, okay, so we're going to call a function this way. We're going to say apply f to the arguments 3 and 4. Then the tree structure there is it's an apply tree. The first branch will be the name of the function. Then the other branches will be the arguments to the function. So in this case, it would be f applied to 3 and 4. Okay? That works down here with a function of no arguments because we'll call it as apply g with no arguments. And then that's a tree. That's a tree with one branch. It's the apply tree with one branch, just no arguments, the name of the function. Okay? So the syntax in our language for calling a function is you apply the function to its arguments. This guy needs to be there. There has to be a function. Notice that this is 0 or more expressions, 0 or more arguments. There may be 0 arguments. See, if this was a plus, that would be 1 or more, but we're allowing 0 arguments. Okay, so apply the function to arguments. Okay, so the reason for the apply is just this little technical glitch that if there weren't any arguments, okay, if you have a function with no arguments, calling it, well, it works fine here, and it works fine this way, it works fine this way, it works fine this way. Well, it doesn't work fine here, but Scheme has its own way of dealing with this. In the Scheme, this is where Scheme and Lisp and Closure diverge from being a true tree language. Okay. Notice that plus can't have no arguments. You don't have to worry about that. Okay. You can't call the plus function without arguments. Okay. So with the plus function, you don't have that happen. But you can have functions that don't take arguments. And then we will still have a tree. The root of the tree will be the keyword apply, then the first branch will be the name of the function, and then any other branches would be the arguments to the function. Okay, so we get around this little glitch that notation, which is the right notation in Scheme. In Scheme, if you call or Lisp, if you call a function with no arguments in Lisp, you wrap the name of the function in parentheses. Okay, and this one is actually a little bit tricky, even for that language, because there's a question of what comes after that thing. If you look in languages like Haskell, sometimes you actually end up having to put parentheses around it like this also. Even in that language, you sometimes have to group the function call. But then that is grouping, not the function call. But even in these languages, functions with no parameters can get a little bit tricky. This is real straightforward. That's one of the advantages of the math notation, the Scheme of the Java. That's one of the advantages of the math Java C notation. It's real clear that you have a function with no arguments. Okay, and ML F# Haskell notation, it's a little bit tricky for them. Okay, and this is the Scheme notation, the Lisp notation, and it's not really a tree. Okay, and then this will be the language 7 notation. Okay, so the language 7 notation that we're going to be using says apply. Okay, so this is the language 7 notation. Okay, and actually, I looked. There are languages out there that make you write this. I actually found real, honest to goodness programming languages that use the same notation. They apply a function to the arguments. Okay, because function application is the technical term for calling a function. Calling a function is called function application. Okay, you can see function application. There's a Wikipedia page. It's the act of applying a function to its arguments. People in C and C++ and Java tend to call it a function call. See, there's the traditional math notation. There's the Haskell-like notation. Okay, they don't give any of the other notations here. So there's the traditional math notation, which was adopted by C, C++, and Java. Actually, this notation is used in some math books also. The notation of just writing the name of the function followed by the argument, that actually is used in a few math books, not very many. But Haskell adapted it. In ML, the functional languages like ML, Haskell, and Clojure, not Clojure, ML, Haskell, and F#, they adopted that notation there. Okay, all right. So apply is the fancy word for function call. Okay, so I use the apply keyword. I could have used I could have put, I could have said call F with 3 and X as parameters. I could have made the syntax for the language call here, but I used a more functional like word. I'm trying to use the terminology that's used more in the field of functional programming. So I called it apply, just because that's the word they're more likely to use in functional programming. But then I looked and I found that there actually are languages out there that use this notation. Okay, I can't remember which. Can't remember one of the ones I found that used that notation. Let me see. I thought no, I can't remember which one. I thought it was Tickle. That's an old language from the 80s and 90s. No, I can't remember what language it was. Thought it was, but there was a language that was, it was a language that was kind of I remember it was a language that I knew about. There was a language that was used like 20 years ago, a reasonably used language 20 years ago that used this apply notation. Okay. Oh, and this apply notation is actually underlying, if you looked at the output from many compilers, they actually do exactly this. When you compile even languages like any of these, like if you compile C or Java or Haskell, if you dig deep inside the compiler, you see them actually compiling function calls to apply a function to its arguments. Okay, all right. So that's part of our notation that we're going to, in our case, it's really to get around the no argument function. Okay, if we required every function to have arguments, if we required that every function have at least one argument, then we could have just used the notation that Lisp uses, because that would, if there's at least one argument, then you could make the name of the function the tree root, okay, and then the branches would be the arguments. So that would be the root of the tree, and those would be the branches of the tree. And that would work fine if there was guaranteed to be at least one argument. But when there's no arguments and you get this, it's kind of messy. And I wanted to avoid that messiness, so I threw in this extra keyword. Okay, and that just kind of simplified things a little bit. Okay. All right. So that's half our notation. That's our notation for calling a function. Okay. Okay. So I'm going to save the notes. Okay. Now, what about defining a function? Okay. Let's just do some examples of it. Let me build the. Oh, it's already built. Okay. Okay. Now, the way we're going to define a function is say the keyword. Okay, you declare a variable by saying var x5. Okay, and then we see it get put into the global environment. There's the variable x. There's its value in the global environment. Okay. Okay. Now we'll use the keyword fun to declare a function. So function f. Okay. Now the question is, what should go afterwards? Okay. I wanted, again, I got a little bit of problem with having trees. Okay. So here's what you might want to do. Okay. I'm not going to be able to do this. Okay. I mean, this is what you do in math. Okay. Okay. Or let's go back to the function of two variables. Okay. There's a definition. Okay. That's not using tree notation. Okay. You could turn this into tree notation by, let's see, what's one way to do it? We somehow want to turn this into a tree. Okay, we want a notation that's going to turn this into a tree. What we're going to need is a branch that says, here's the name of the function, branches that say these are the arguments of the function, and a branch that is the body of the function. So we need at least we need at least one branch. Okay. Well, actually, we need at least two branches. We need a name and a body. Now, remember we had the case of f g equal 5. Notice it doesn't have any parameters, but it does have a name and it does have a body. It's got to return something. So we need at least a branch for the name of the function and a branch for the body of the function, and then branches in between, if there are any, which would be parameters. So one branch for name, one branch for body. That'll be the first branch. That'll be the last branch. And in between branches will be the parameters. Now the thing is, we need to hang them off of something. So what we'll hang them off of is this keyword fun. So fun will be at the root of the tree. So we'll have this tree rooted at the keyword fun. Its left branch will be the name of the function. Okay. Its right branch in this case is going to be a addition of this is the body now. It's the addition of multiplication with the variable y. Oops. This is a product, and over here is the variable y. And then I'm taking a product of, what is it? X with itself. So x squared. Okay. So notice that this tree is acting as the body. Okay. So I have a function tree, which is defining a function. The left branch is the name of the function. The right branch is the body. And if there are branches in between, they are parameters. Okay. So in this case, it's got a parameter x and a parameter y. Okay. All right. Now that would be okay, but I actually made it a little bit different than this. Okay, so that would look like the following. I would be I'm saying function f, x, y, and then the body is the sum of the product of x with y. Okay, that's the body. Let's see. That's the body. So then I would close it. So there would be my function definition. Okay. I could have gone with this, but I decided for technical reasons that have more to do with what we're going to see in language 8 to do something where I'm going to separate the name of the function from the actual definition of the function. In a sense, this guy is somehow separate from the, whoops, that's a y. There's a little bit of a fundamental difference between this thing and this stuff here. Okay. If you think about a variable, when you say var x, say the product of 4 with 5, okay, there's two things there: the variable and its value. Two things: variable and value. So you say this is a tree, var, it's always got two branches, a left branch and a right branch, always. Okay. The left branch is the name of the variable, and the right branch is the value of the variable. Here, the value of the variable is a tree, the product of 4 and 5. Okay. But a var only has two branches. And I want fun to be like var. I want to say that I'm saying, here's my function, here's its value. Like, here's my variable, here's its value. Okay, so that means I want all this part of the tree to be I want this part of the tree to be wrapped by itself. And we'll see that this is actually a really good idea, that we have to separate the function name from the function value. Just like here, there's the variable name and the variable value. This is kind of blurring together the name and the value. And that's actually true up here too. This kind of blurs together the name of the function and the value of the function. Okay. So here's the notation we're going to use that tries to separate. It wants to be more like this. Okay. So here's what we're going to do. You say fun for function. F is the name. Then over here it's going to be the value of the function, and then you're done. The question is, what goes in here? What goes in here is going to be essentially all this stuff here. And it's going to be prefaced with the keyword lambda. Okay, so it's going to be a lambda, what we call a lambda expression. Then the lambda expression is going to say parameter x, parameter y, and then body. And the body, I'll just copy and paste it here. Notice it. See, all this becomes the lambda expression. See, I'm taking that and I'm wrapping it in a lambda. Oops. Okay, now this last parentheses is closing the definition here. And this second to last parentheses is closing the lambda. And if I did it right, let's see, I need to close the plus and the multiply. That closes the multiply. That closes the plus. Okay, so there's the body. Okay, there's the body. Okay, so there's the lambda expression. See, there's the lambda expression. And now I have a structure very much like up here. Var, name, value. Fun, name, function value, which is something we really want. We want function values. Okay, now you may have heard of lambda expressions. Lambda expressions are at the heart of modern programming. So Java now has lambda expressions, and C++, C Sharp has lambda expressions. C++ has lambda expressions. All of these languages have only recently added lambda expressions to them. What we're trying to do over here is really do what modern programming languages are trying to do. This is old-fashioned notation. It's math notation, and programming languages adopted it straight from math. It turns out not to have been a good idea. It turns out as we do, especially when we go to language 8, which turns out to be, language 8 is trying to be a modern functional programming language. We'll see this is not great notation. It blurs the name of the function and the value of the function. It essentially does this, and it kind of like, it doesn't do this. It doesn't do name value like we do with variables. Name value. What we need is a function value, which is what lambda expressions are. Lambda expressions are a way of having function values. Okay. There you see they're all over the place now. Every modern programming language now has lambda expressions, which let you define function values without saying what their name are. It separates the function value from the name. Later on, we'll see that we're going to be able to use this guy by itself. Later on in language 8, that will be something we can use by itself, just like in C++ and Java. That's a function value. That's the function of two variables, x and y, that returns the x squared plus y. Okay. If you were to use math notation, here's a notation you'll see in some math books. This guy will be written the following way. F is the name of the thing that takes in x and y and gives me out x squared plus y. Okay. This is naming something. It's naming x. It's naming f. F is the thing that takes in two parameters and gives me back that result. This is called a lambda expression, or an arrow. Some people call them arrow expressions. Okay. Now, in this notation, the parentheses are kind of redundant. I don't really need them. So I can just say f is x. Well, okay, comma means there's another parameter, y. No, I see the arrow. So now I'm done with parameters. So now I'm giving you the body. If it took 3 parameters, okay, parameter, comma, that means there's another parameter coming, parameter name, comma, means there's another parameter coming, parameter name. Oh, there's then after the Z, there's no comma, and you see the arrow. So that means, okay, what follows now is the body of the function. And then if I want, I can use the other variable. Okay. Now, this notation has problems when a function doesn't have any variables. Okay. This notation has a problem. That's not very readable. So you're back to the parentheses like that. Okay, so if the function actually took in no parameters, like our G, we would write G equals no parameters, always gives us out 5. Okay, but I'm separating. Now, this is a tree. It's an equals tree assigning to G that lambda expression. This is an equals tree assigning to F on the left this lambda expression on the right. Okay, so this is called, and this notation is actually the notation that C++ and Java use for lambda expressions. If you go look up the lambda expressions in C++ and Java, they're written very similar to this, except they put, well, Java puts the parentheses there. Java keeps the parentheses. C++ is weird. C++ uses a very weird notation for its lambda expressions. See if there's an example. They're almost unreadable. They picked like the weirdest notation. See if I can find somebody who's got a good C++ lambda. Okay, see that empty pair of square brackets? That begins the lambda expression. See, here's a little table of what's going on. You use a pair of square brackets, empty square brackets, to say this is the beginning of the lambda expression. Then there's the parameters in parentheses. And then in this case, they're using braces, though you don't have to use braces for the body. So here they're using braces to mean here's the body's in braces. So it would, in C++, this guy here in C++ notation would be something like F equals square brackets, parentheses, x comma y comma z, then brace x times x plus y times z. Okay, close brace. Okay, that would be the lambda expression, the function by itself, and that would be the name for it. Notice that we've clearly separated name from value. This notation up here doesn't. Here's the name, but look, in between the name and the actual value, look how everything's scattered up. Name, parameter list, equal, value. See how it's all jumbled up? Notice what we unjumbled it up. We put the name by itself on the left of the equal sign, and essentially combine the parameter list with the body of the function on the right of the equal sign with an arrow between them. That's like the clearest notation. You unravel this by putting the name by itself on the left, then the parameter list separated from the body, but with an arrow. Now, in C++, they did kind of weird. They just have the parameter list next to the body, and then they put a pair of square brackets up here to say, we're about to give you a lambda expression. This empty square brackets are the announcement that you're about to get a lambda expression. Okay. Java notation is actually pretty much like this. Okay. So this would be C++ is more or less like this, and Java is more or less like this. Let's see. So you can find a simple lambda expression. See, parameters, arrow, expression. See, syntactically, it's real simple. Parameter. Now, parameter is actually now, if there's one parameter, you don't need the parentheses. If there's more than one parameter, you do need the parentheses, the way they decide it. So if it's parameter, arrow, expression. And if there's more than one parameter, you put them in parentheses. Okay. You can, if you want, put braces around the right-hand side and make a code block. Okay. And like here's a real simple lambda expression. N goes to system.out print line n. Now here they use the braces. I don't think they didn't have to. I don't think they had to use, because there's just one statement in there. I don't think they had to use the braces. Okay. So the lambda expression in Java is real close to this more or less abstract kind of notation. This one here. Then there's lambda expressions in, you can do this in all modern language, like you write the word lambda, arguments, colon, expression. Okay. Now, so they use the word lambda. That's what I'm using here. See, I introduced the word lambda because it's very common to use the word lambda. See, that's in place of this empty square brackets in the C# in the C++ notation. The C++ people used empty square brackets. The Java people just dropped the word lambda from their syntax, but the Python people keep it. So you say lambda, arguments, colon, expression. Okay. So here, x is, now notice this is funny. X is the name. That's the function. The function is a lambda that takes in one variable. And what does it do to that variable? It adds 10 to it. Okay. So there's the function, and it's called x. And then here you call it using regular function notation, x of 5. Okay. Here's another lambda. This one takes in 2 parameters, no parentheses, lambda, variable, comma, variable, colon, to separate the parameter list from the body of the function. And then there's the body of the function. Okay. So there's Python lambda expression. And you can do like JavaScript. JavaScript has another slightly different notation. If you bounce between these languages, it gets confusing as heck to try to remember, whose lambda expression am I using today? They call them arrow functions in JavaScript, and they use this notation, an equal arrow. They use not, other people use the simpler single, minus sign greater than for the arrow. They use equal sign greater than for the arrow. Okay, so you write variables greater than equal, or equal greater than, which is the arrow, and then the return value. Okay. Let's see. They have some more examples. Okay. Notice here they put parentheses around the A, but they don't have to. But maybe if you have more than one argument, you may have to. See, here, there's 2 arguments to the lambda expression. I think when there are 2 arguments, you do need the parentheses. If there's only one argument, the parentheses is optional. If there's 2 arguments, I think you put a parentheses and a comma between the arguments. And then you separate the arguments from the body using an equal greater than sign. And they tend not to call them lambda expressions. They tend to call them arrow functions. But notice I Googled lambda expressions and I got JavaScript arrow functions. And here, JavaScript's lambda. Oh, I don't know if they make. I don't know if they have a difference between lambda expressions and arrows. JavaScript's a bizarre language. There's actually too many ways of doing everything. There is this notation here, the function notation. That might be what they're calling lambda expression. Then this is the notation that doesn't see this notation and this notation are both they're similar. You can call this a lambda expression because there's the name, there's the function value. You're just using the word function instead of the word lambda. And then here's the parameter list and here's the body. So this is one notion of a lambda expression, but then there's this other notation here that uses this arrow notation. So the arrow, I think in JavaScript, the arrow functions are one kind of lambda expression that use this symbol. And what they call lambda expressions is this other notation that uses the word function. And as far as I know, I think they're the same thing. I think this and this, I'm not positive, but I think there may be two notations for the same thing. But JavaScript being the bizarre language it is, it's very possible that this has quirks that are different than in JavaScript, everything has a quirk to it. Everything is kind of messed up in the design. So it could be that this thing acts funny in different ways than this thing acts funny in different ways. JavaScript is the weird language. Almost everything in it acts funny in some way. So it's very possible that this and this have their own quirks to them. Okay. And I use the word quirks actually in a technical way. I don't know if you know it. There's something in JavaScript called Quirks mode. JavaScript is such a bizarre language. It even has Quirks mode because you need control over all the bizarre quirks in the language. So you actually have Quirks mode in JavaScript. The language has just really got too many things that are a problem in it. Yeah, the language has picked up so many little quirks that they even had to come up with a way of controlling them. So you can set the Quirks mode in JavaScript. And I don't remember if these two things are absolutely synonymous, this way of writing a lambda expression and this way of writing a lambda expression, if they're actually completely synonymous, or if I have a feeling they're not. I have a feeling that this thing acts slightly differently than this thing does. But the key from our point of view is you're separating the name from the function. See, on the left-hand side, the equal sign is only the name. And on the right-hand side, the equal sign is everything you need to know to say what the function is, except the name. Same here. There's the name. Then on the right-hand side, the equal sign is everything you know to call the function, except the name. Now, okay, but you can call it using that name. Turns out you can even call it anonymously. We'll see in a little while when we get to our language 8 that you can actually use these guys anonymous. See how they called it anon? So they named an anonymous thing. That's like saying my name is anonymous. You know, I'm an anonymous person because I name myself anonymous. But yeah, they're being kind of dumb here. Okay, so this is often called an anonymous function because you can actually not give it a name and use it anonymously. We'll see how to do that in language 8. But here, whoever wrote this said, oh, I'm going to call it anon because it's an anonymous function, but I've given the anonymous function a name, and the name is anon for anonymous. Okay, that's not very clear. That's really muddying up too many ideas here. But the key is that this separates name from function value. Okay, so back to our notation. I could have done this, which would be very Java-ish likely. So a function is name, parameter, body of the function. And then I'd have this tree, which would have worked. But I wanted to be more modern. I wanted to separate the name from everything else. So that gives us this notation. Now the tree looks like this. A function definition has always two branches, the name of the function and the value of the function. There's the name. The value in our case is going to be a lambda. A lambda means the value of a function. Now the lambda has now there's as many branches as there are parameters, and then there's always one branch that's the body. So the lambda always has at least one branch, which has to be the body. So if the function is, so here I'm defining f. So when I'm defining f, it's going to be parameter x, parameter y, and then the body is the sum of, what was it? The product with y of x times x. Okay, x times x. Okay, a lambda expression always has first the parameters and then the body. Now for G, it would look like the following. For G, I'm defining a function. Function like var always has two branches. You're defining a name and a value. Okay. For G, there are no parameters, and the body is just 5. Okay. So G is the function that takes no parameters because there's no branch. There's only one branch. That's the body, and the body always returns 5. So there's the definition of G. Okay. Later on, we're going to make these lambdas independent of things. We're going to make these lambdas live on their own. We'll make function values. The fancy term is we're going to make function values first-class values in the language. We're going to make functions first-class values in the language. Right now, functions are not first-class values. So this is C. You know, we're really building a model for the C language. And then when we make these guys first-class values, when we make the lambdas live on their own, then we've drifted from C to modern functional programming languages like ML and Haskell and Scheme, okay, and JavaScript for that matter. JavaScript has modern, you know, and also we're going to go from old Java to new Java. Okay, if you go to, or C++, Java adopted Lambda expressions in Java 8. Java got Lambda expressions in Java 8. Okay, when was Java 8? It wasn't that long ago. 2014. Okay, so that was when now that was 20 years after the language had been invented. The language was invented in the early 90s. It was first released officially in 1995. That's easy to remember, 1995. But it had been in development for a while before that. So at 20 years after it was released, it finally got Lambda expressions. Okay, Lambda expressions existed in functional programming languages back in the 60s and 70s. So it took a long time for Lambda expressions to get into Java. And C++ is similar. C++. See, what year does C++ get lambdas? Oh, 2011. Yeah, C++ 11. That was the big, that's C++ 11 is like Java 8. Java 8 is when the Java language started saying, we're really going to modernize the language aggressively in the direction of modern functional languages. It started with Java 8, and it's still ongoing. An aggressive modernization of the Java language started in 2014. And in the C++ case, it started in 2011 with C++ 11, and it's still an ongoing process. Okay, so that's when Lambda expressions were added to. Now Python, let's see, JavaScript had Lambda expressions from the start. JavaScript's in some way, I make fun of JavaScript in a lot of ways, but in a lot of ways, it's an interesting language. It had Lambda expressions from the get-go when it was first released. Now, what about Python? I think Python added them later. I can't. I don't know if let's see. I don't think I have time to see. They're mentioning Lisp and Scheme. See, these ideas came from Lisp and Scheme. See, there's our tree notation. Oh, I don't have time. Okay. Another one's C#. C# got Lambda expressions around the same time that Java and C++ got them. I think it was C#3. Yeah. So C# got them after both Java. What was it? 2007. Okay. Okay. So you know, it's relatively recently that all these languages started doing this. You know, Java. Yeah. So actually, C# beat the others. C# got it before Java. I thought C# got it around the same time. Um, that's actually quite a bit earlier than either C++ or Java. I have a feeling that those were originally very limited Lambda expressions. My memory is that when C# got Lambda expressions in C#3, they had lots of limitations to where you could use them and stuff like that. Okay, let's see. Do they have an example of the notation? See, there's the notation. See, they use the same arrow as JavaScript does. See, they kind of use the JavaScript arrow. Oh, I was going to show you. In C#, Lambda expressions are closely related to what are called delegates. If you've ever done any C# programming, you've probably heard of the phrase delegates. And Lambda expressions are related to C#. Oh, there's the word delegate. Okay. Lambda expressions are, you know, the C# language uses the word delegate in some places where we would normally use the word lambda expression. Okay. All right. So it's something that existed in functional languages back in the 60s and 70s took until recently to finally enter mainstream programming. So we're talking C#, C++, Java. C will never get this. No one's ever going to go and put these features in the C language. So they're putting them in Java. They're putting them in Java. They're putting them in C++, putting it in C#, Python. Nobody's ever going to go back and change C. Well, I shouldn't say nobody. They might. Yeah, maybe they will, but probably nobody will use it. Okay. But so C is just too old a language to be adding these features to. Okay. And it would probably be just too hard. Okay. So now, we'll see that we're going to break that off and make it live on its own. Like right now, it only lives as part of a function definition. A function definition is a name and a lambda. Okay. And the lambda is just there for future. If it wasn't for the language 8, we probably would have used that notation, which is the older C, C++ Java notation that blurs the name of the function with everything else. See, it's not separated. You're just saying a function has that name and those parameters and then that return value. Okay. It doesn't clearly separate the stuff that's the function from the name. Just like this notation, name, stuff that's the function, the assignment's really assigning to that name. And what's it assigning to that name? The function that takes these inputs and gives me that output. So you notice how that's very mangled up notation. Okay, it's very mangled up notation. So this cleans it up. Okay, name equal lambda expression. Okay, name equal lambda expression. Okay. Oh, and why are they called lambda expressions? Okay. The first person who thought of this idea of clearly separating the name from the definition of the function, who wanted to get away from this mangled notation, was a mathematician in the early 20th century. Well, there's this thing called the Lambda Calculus. See, Lambda Calculus. It was invented by this man, Alonzo Church, in the 1930s. He's the guy who said that we should, for theoretical, he was studying mathematical logic. And he said that to make the study of this stuff clearer, it would be useful to separate the idea of naming a function from defining a function. And he separated them. And then what he did when he separated them, he needed a way to say, he needed, see this part here that says, well, he wanted a notation that would essentially say, it's actually, he used a notation similar to this. He wrote lambda. He wrote the letter lambda. That announced the fact that you were going to have a lambda expression. Then he wrote the parameters, separated, and he wrote the parameters. Then he wrote a dot. Then he wrote the body of the function. So his notation was lambda, but the symbol lambda, then variable, then dot, then body. Okay, so it would be something like this. His lambda expressions would look like that. This would be the Greek letter lambda, then variables, dot, body. Okay, and he called those lambda expressions. So here's some of them written in, see, lambda takes in one parameter m, and then that's the body. Okay, yeah, it's not very easy to read. Like, here's a complicated lambda expression. Okay, so that's kind of a complicated one. Since then, the name stuck. He picked the letter lambda for whatever reason. He just needed a letter out of the alphabet. He picked the Greek letter lambda as the thing that says, I'm starting the definition of a function. And people called them lambda expressions. He called it Lambda Calculus. And 100 years later, we're still talking about lambda expressions in our programming languages. Okay, but it came out of this branch, and this branch of mathematics has become really important. He invented it back in the 30s before computers existed. Modern compiler theory is all based on lambda calculus. If you go look at what people do in research in compilers, what they do is lambda calculus. They use this as their language for describing work in compilers and programming languages. Okay, and this is it's not trivial stuff. It's very advanced, a branch of mathematical logic, but it's become the foundation for modern programming languages. Okay, and we use it all the time in this idea of lambda expressions. Okay, lambda expressions came out of lambda calculus. Lambda calculus is still the theoretical foundation for modern programming languages. Okay, if we didn't want to do language 8, we'd use this notation because it's good enough. It is a tree. There's the branch, there's the root of the tree. First branch is the name, middle branches are the parameters, last branch is the body. That would work, but I wanted to separate the name from the value, especially because of what we're going to do in the next language. So instead of using that notation, we're going to use this notation. So this is now the language 7 notation. It's also going to be our language 8 notation when we get to language 8. So it'll be the notation. It'll be the notation for both language 7 and language 8. Okay. 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 So this one, this syntax could work. So here's the way to say it. This syntax could work, but we want it to be more modern than that. Okay. This syntax here okay, it's too old-fashioned. Okay, this this notation is just a little bit. This would be a little bit too old-fashioned for us. Okay, this would be a little too old-fashioned for us. Then this notation, very modern. Okay, separate the name from the thing you're naming. So a function always has two branches, just like a var always has two branches. The thing you're naming and the value you're giving to it. The thing I'm naming and the value I'm giving to it. Okay. Eventually we'll see that we don't need var and fun. Eventually what we'll do is we'll go var here, because this is just another variable name with a value. Our goal is to replace the word fun with the word var, and that turns out to have profound effects on the language. Okay, right now we need a special keyword there because we're treating functions as a special thing, but eventually we're going to make these lambdas independent values on their own, and then we'll be able to write the word var there and say, oh, my variable f names a lambda, my variable x names a number. So var x is a number, var f is a function. That's our goal. Our goal is to get rid of the fun keyword and replace it with just var, and you'll just only have the var keyword. The language will only need the var keyword. Var will give a name to a value, and lambdas will be first class values in the language. Okay, let's see. Okay, all right, so all this explains the choice of the notation. So all of that was to explain the notation for apply, okay, which it needs this one. Remember, it needs this mostly because of functions with 0 arguments. Yeah, that was just to clean up that was just to make the notation for functions with 0 arguments work a little bit better. What's more important is the fun notation needing the lambda, because eventually the lambdas will live on their own. Okay, lambdas will move down. Notice that lambda doesn't appear in this part. In language 8, we'll have lambda there, and fun will disappear, and then the language is really different. In language 8, essentially get rid of that and move lambda there, and then all of a sudden you have essentially a modern functional programming language. Those two little changes are going to make a profound difference to us. Okay, get rid of fun, won't be needed anymore because we'll use var for all variable declarations, but we'll need to move lambda down here and make it a first class thing. It'll become an expression. Right now, lambda is just a little sidekick to fun. Okay, right now lambda just lives only right there inside function. It's the right hand side of a function variable lambda. Okay, so right now it only has the effect of changing this notation, which is what we would have done otherwise, to, where is it, this one. Okay, it's giving us a slightly, we would have done this otherwise. We would have done that, but we want to be ready for language 8, so we're doing this instead. But right now, the lambda is just a kind of a fancy way to write this. Okay. So another way to put it, in this language here, I could have just taken those guys and then gotten rid of this. That would work. Fun, name of the function, 0 or more arguments, names, and then the body. Okay, see, that would work. That would be the notation for, that would be the notation for this tree here. That would be this notation. And it could be made to work. And that would be, but that'd be too old-fashioned. You can't separate the function, the name, from the rest of this stuff. Okay, so we're not going to do it that way. We're going to do it this way. So all I'm doing is, this here stands in for that stuff there. See, now this just stands in for that. Okay, but in the next language, this becomes an important piece of the language all by itself. That's what we're really wanting to get ready for. Okay. Oh, I said, when you say lambda symbol represents branching, the answer is I don't think so. I don't think it had anything to do with the idea of branching. You're right.
I'm just saying it resembles it, not represents it.
Yeah, but see, function, you think about function calls do sort of send you someplace. I think it was purely happenstance that he just picked the letter lambda out of the air. Yeah,
could be.
Historically, there was no meaning to lambda. Oh, and the lambda symbol is kind of taken on mythical proportions. Okay. Oh, I'm sorry. There's a famous website, Lambda the Ultimate, which is a really good place to learn about programming languages. The Programming Languages weblog. Lots of really good people right here. Very interesting stuff. The most famous book in computer science programming one of the most famous books around, Structure and Interpretation of Computer Programs. Look what's on the front cover. This book was written back in, like 20, 30 years ago. See, the wizard with a lambda. Okay, this is one of the books that this is the book that introduced the scheme programming language. Okay, so this book introduced the scheme programming. It's from MIT, and a lot of people still swear by it as being one of the most important computer science books you could read. Okay, and there's a lot of other books now that they put lambdas on the front cover. But I think that was the first book where they actually put a lambda like that on the front cover. Okay, so lambda is become the symbol for modern functional programming. Okay, if somebody, this letter now kind of simple, like Lambda Expressions, Lambda Calculus. The Greek letter lambda now sort of kind of stands in for modern abstract functional programming. Okay, now that's a lot about the syntax because there's a lot of history to this syntax. So I kind of wanted to explain it real well because the syntax is quirky. Why would I have kind of like why would I do this and why would I do this? The reason for this was only because of a quirk in the need for functions of 0 parameters. And this is really there because I want to set the stage for doing something more powerful. If I didn't want to set the stage for a language 8, I wouldn't have this one here. I would just put these guys right in there. And again, like I said, then I'm using this notation instead of this notation, which is fine. This notation is good enough for Java and C and C++ like languages. Okay. Now over here, then here's what it looks like. Function f is a lambda, and my function f, I'll take in x, and I'm going to write the squaring function. So there's the squaring function. Okay. Notice that f is now in the global environment. See, and it's got a value with a lambda tag, and now there's an integer tag, a Boolean tag, and a lambda tag. Okay, so now the integer value doesn't matter. Since the tag is lambda, the integer value doesn't matter, the Boolean value doesn't matter, and I look to the L value, the lambda value, and it's pointing at the body of the function. See, there's the body, there's the name, there's the body. Okay, now notice that there's no real reason why I can't give this value some other name. At this point, the name is really separate from the value. And I could, why not call it G? And we'll see that that's kind of what we want to get at, that there's no real reason why this value can't be the value of, why can't I have some, I can just change the name of it. In the language like C and C++, there's no way you can change the name of a function. If you think about it, in C and C++, when you define a function with notation like this, suppose you decide halfway through your program that you want to rename the function G. There's no mechanism for that. There's no mechanism for, you can rename variables. If you have x is 5, you can just say y equals x, and now y represents that value. But there's no way that you can change the name of a function. But if you think about it here, that value, there's nothing in it that's, f is nowhere in there. So why does it have to be called f? You could just as well call it G too. Okay, so we're separating the name from the value. Now I can apply f to the number 4. Okay, and that's what we'll talk about next week, is what is going on here. Notice that I have a function activation record. This is the key thing. The function activation record bound 4 to that that x there. See, that 4 is the argument, that x is the parameter, and I need an activation record that binds the value 4 to the formal parameter. Okay, so, and then that activation record, this is like the stack frame in Java and C++. That activation record is connected to the global environment. Okay, so let me show you how that could work. Suppose I have a variable x in my global environment. Okay, x has the value 5. So one last trick. Fun G. What's G? I'm going to make G a lambda expression, that takes in a y, and what it does is it's going to add x to y. Okay, so function G is a lambda expression that takes in a parameter y, and it adds x to y. But wait a minute, what x? What x would that possibly be? In this lambda expression, I'm adding x and y. Y is that parameter. Where's that x? What should I do with it? What do you do in C and C++ and Java? How do you evaluate that? When you get to here, what x do you use?
The x equals to 5.
The global x.
Yeah.
The global x. Just like that's what you would do in Java. If you have a x that isn't a parameter, you look for a global x. That's what C, C++, and Java all do. That's called a non-local reference. It's not a local variable, so you look for the global variable. Okay, so then this would give you 5 plus 5 is 10. Okay, same here. Now look, see this x here is that x. This X here is that X in the global environment. Now let me call the function G of 3. Oopsie. Now I want to apply G to the input 3. Okay. Now look, I got an activation record that binds Y to 3. But then when I evaluate this guy here, Y is in that environment, but X is follow the arrow up to the global environment. So the global environment holds X, the definition of F, and the definition of G. Then the activation record for the call to G holds the binding of Y to the parameter, the argument, the formal parameters bound to the argument, but then this variable gets looked up in the global environment and it's there. So the result was 3 plus 5. So the result was 8. Okay. This interpreter lets you watch things happen. Like I wish Java would have, I wish somebody would write something like this for Java. Notice it lets you watch the stack frames essentially be created and destroyed. You're seeing a stack frame here. Okay. And if I did, let's see, do one last example. Suppose I apply, let's see, F to apply G to, say, 8. Okay, so the result of applying G to 8, that's the input to F. And if you follow this, you can see that first you call G, that's this activation record. Then when it returns, you have to call F, that's this activation record. See, this activation record had a Y in it because G has the formal parameter Y. This activation record had an X in it because I was calling F. Okay, so you called G, that pushed an activation record on the stack. Then when G returned, the activation record was popped off, and then another activation record was created. Okay. Yeah, and we'll play around with this more. We run out of time, but that's what we're playing. We're going to watch these we're going to watch the language execute by having our own interpreter and being able to instrument it ourselves. We can watch the language do its work, and that hopefully help you see how languages like C++ and Java actually work. Now they do all this in assembly language. They're doing all this on the CPU. We're doing this in Java. They're actually doing it in the CPU, but the ideas are very much the same. You know, this is the stack, and the stack, you know, this was a stack frame, and this was another stack frame. Okay, all right. So that's what we're going to playing around with. So on next week, we'll start looking at the actual implementation of these things. The actual implementation of the fun thingy in the evaluator. Okay, in the evaluator, we're going to read if handle fun. Notice it doesn't say evaluate fun. Fun's not an expression, so you handle it. Returns void. It's not an expression. So fun, and then apply. Okay, so heavily documented. I've spent a lot of time writing the documentation. Notice that this function is 90% documentation. If you strip out all the documentation, there's only about 5 lines of code there. Okay, it's 90% documentation because it's trying to explain to you all the steps going on in a function call. What is a function call really doing? And I even numbered the steps to try to make it easier to understand what's going on. Okay, so we're going to go through that code real carefully. And you can strip out all the comments from this, and look, you'll notice that there's not much code. And then after you strip out the comments, you can strip out the runtime tests, which really don't need to be there. And then you find out it's only about 5 lines of code. That it's simple idea, but most people don't understand it. It's actually a very simple idea, but unfortunately, even a lot of programmers don't really understand what's going on when they call functions. So that's what we're going to talk about. That'll be next week. All right. So run out of time, should quit now. Okay. If you have any questions about the new homework assignment or the previous homework assignment, come to office hours or send me an email. But your current homework assignment is for you to do something with language 6 that's going to help you understand what we're doing here in language 7, because you're going to have to implement that for loop, which has its own environment, and that gets you thinking about the environment. And this is all about environments here. What the real work here in this eval is these activation records, the activation environments. Okay, so a language 6, the program assignment 3, which works with language 6, is meant to help you understand what we're doing in language 7. Okay, anybody have any last second question? Any last question?
A question about the naming the lambdas is using like a different function pointer similar to renaming in a sense, or?
Yeah, that's a real good point. You could say that's like renaming, because you can actually create a new function pointer to point at a but you can only do that in C. You can't do that in Java.
Right.
So, but it's not very deep. That's a real shallow, tricky thing to do. It's not really what we want to do. So you're right. Technically, you can create a new name for a function by creating a function pointer to it, and that's just kind of like a party trick. It's not very deep, and Java won't even let you do it, and C# won't let you do it. Okay, but it does get close. It is a good point, because it does really point out that it's just a pointer. See, in a sense, this guy is just a pointer to something. There's the value. So in a sense, there is very much just a sense of these things are just pointers. And that will be an important, we'll make real use of that idea. The key there's not so much that you could rename it. The key is what you said is it's a pointer. That what the function is really it's a pointer to something. And that's important. So realizing that a function, that the name is really a pointer to the code will be important to us. Okay? But Java doesn't let you do it. Java doesn't let you do that trick. C will let you do that trick, but it still not what we're doing here. It's not separating the name from the value. It isn't really doing a lambda expression. Okay, it is kind of doing this because it lets you pick any name to point at that thing in memory. So C will let you create any name you want to point at that thing in memory, but that doesn't let you do very much with it. Okay, well, we're gonna end up doing a lot more with it than that. Okay, any other questions? Okay, I'll quit sharing, and we'll meet again on Monday. Have a nice weekend, and if you got questions about the homework, send me email or come to office hours. Bye.
Bye.